Welcome, and get ready to dive deep into a topic that's quite literally shaping our future: wireless communication in 2030 and beyond. So, we just got 5G, right? And it was and still is a massive leap forward in mobile broadband. So why do we need a new generation so quickly? What are the inherent limitations of current generations, particularly 5G, that are putting pressure on us to change?
Is 5G truly enough for the highly anticipated and often extreme demands of 2030 and beyond? According to the Alpert Research Team's comprehensive report, the answer is a definitive no, and it's due to several key fundamental limitations inherent in current 5G deployments and its underlying architecture.
Okay, what are they?
First, let's talk about congestion and scaling. While 5G offers impressive peak speeds and greater capacity than 4G, it still struggles significantly with congestion in dense urban areas, especially as the number of connected devices and the sheer volume of data traffic continue their exponential increase. The Alpert report cites projections showing data traffic escalating dramatically, potentially reaching 282 exabytes per month by 2027 alone.
282 exabytes. Wow.
Right. This exponential growth presents unsustainable scaling challenges for current 5G architectures. As more and more devices connect, and as emerging use cases become increasingly data-intensive, think high-definition AR/VR streaming or real-time digital twin updates, 5G networks can quickly become bottlenecks. This severely impacts overall user experience and network performance, leading to frustrating slowdowns and service degradation. Critical communications, in real-world scenarios, this ambitious target is often unmet. But a more critical issue for next-generation applications is that jitter, the variability or inconsistency in latency, is not deterministic.
Not deterministic, meaning unpredictable delays.
Exactly. This non-deterministic performance makes 5G fundamentally inadequate for a new wave of emerging, highly sensitive, and time-critical applications. Imagine haptic feedback systems needing instantaneous tactile responses, or remote surgeries where even a slight, unpredictable delay could have severe, life-threatening consequences. Truly autonomous systems, whether self-driving cars or industrial robots, demand not just low latency, but predictable and guaranteed ultra-low latency to ensure safety and precision, which 5G often fails to provide consistently. For example, remote control of automated guided vehicles, AGVs, in dynamic industrial settings requires latencies less than 5 milliseconds to operate safely and efficiently. That's a threshold often beyond 5G's reliable delivery, particularly under load.
Okay, reliability and predictability are key limitations there.
Then there's energy efficiency. This is a particularly significant concern for the long-term sustainability of wireless networks and a major driver for 6G. The Alpert report reveals a stark reality. Despite advancements, 5G base stations, particularly due to their increased densification and reliance on active components for massive MIMO and milling wave, consume significantly more energy than previous generations, up to 3 times more than 4G base stations.
3 times more. That's huge.
It is. This current model is simply unsustainable, both for global climate goals and for the practical economic deployment of infrastructure in remote areas where power access might be limited or costly. And the true insight here, according to Alpert, is that without a fundamental architectural shift, the sheer volume of 6G deployments needed could actually accelerate global carbon emissions.
So it could become an environmental liability. What about coverage? 5G was meant to improve that too.
True, but we still face persistent coverage gaps. Despite its widespread rollout, 5G, particularly in the higher millimeter wave bands, still suffers from sparse and inconsistent coverage due to limited propagation characteristics. Rural areas, deep indoor environments within buildings, subterranean spaces, they often experience significant signal degradation or a complete lack of service. This hinders global connectivity goals, creates persistent digital divides, and results in inequitable access to high-speed communication. That's unacceptable for a truly interconnected and inclusive world.
So the promise of ubiquitous connectivity isn't fully realized yet.
Not quite. And finally, a key limitation lies in AI integration. In 5G, artificial intelligence is often used as an overlay. This means it's applied on top of the existing network infrastructure to optimize certain functions like traffic management or resource allocation. It's not natively integrated into the fundamental network architecture. It's more of an external enhancement. This limits its full potential for real-time optimization, truly autonomous network management, and the kind of pervasive, anticipatory intelligence needed to support the complex, dynamic demands of future applications. 6G aims to bake AI directly into the network's DNA, making it an intrinsic part of its operation, not just an add-on.
Okay, so 5G was a huge leap, truly enabling the mobile broadband we enjoy today. But the future demands capabilities that simply weren't built into its core, especially when it comes to true real-time, deterministic performance, pervasive coverage in every nook and cranny, and critically, sustainability. It's a fascinating and urgent challenge that the Alpert report clearly lays out.
We invite you to explore the full analysis. A comprehensive and detailed review of the Alpert Research Team's presentation on the future of wireless communication is available at the following link.